Good morning, how are you? I'm a bit chilly myself. It's 7:44 AM here in St Andrews this morning, and I'm down at the pier by the harbour with my camera at what you can see is some fairly brilliant conditions, to be honest. It's nice and quite blue. It's even more blue over there, and in that direction there is a bit of sunlight just making its way over the clouds because we are near sunrise. Now, you might ask why I'm up at this stupid time in the morning. Well, the answer to that is so that I can get pictures like this. And the reason that I can get photos like that is because this is what photographers refer to as blue hour. And it's this time before sunrise where we get all these really nice, cool, bluish tones. You get a nice haze of purple behind buildings just above the horizon, and it's right before the sun comes up. But why do I have to be up at this time in the morning to get these photos? Now, I may be a photographer, but I'm also a physicist, so I can explain this using physics. Now, I'm Scottish. We're not really known for beating around the bush, and the short answer is Rayleigh scattering. But while a two-word answer might be good enough for your pub quiz, it doesn't really answer the why of why do I have to be up at 7:45 in the morning to take these photos. So, can we do better than that? Well, I think we can. So, as I said, it's a bit chilly, so I'm gonna go and get back to my flat where it's nice and warm. And let's see if we can answer that question. Why did I have to be up so bleeding early to get out here to take photos like these? Okay, so Rayleigh scattering. What is it and why does it make things go blue or golden? Well, firstly, what do I mean by scattering? Simply put, I mean light being deflected into different directions by some stuff in its way. If there's nothing in the way, then light will travel in straight lines until it impacts something. Perhaps your eyes, that's how you see. When a molecule of gas, in this case an air molecule, be it nitrogen or oxygen, gets in the way of a light ray, it will deflect it onto a different path. It will scatter it. This happens because the electric field of the incident light wave will excite the electric dipole of that molecule and cause it to emit radiation at the same wavelength in a random direction. So, a new direction, hence scattering. This is what we see as scattered light. Why do we get blue hour right before sunrise? For that, we need to turn to the equations of Lord Rayleigh, the discoverer of this Rayleigh scattering. For that, we need this equation. I'm going to be honest, this equation looks absolutely horrible, but if we average it over all of our various angles that we could scatter into, we get this. This is our equation for the scattering cross-section, and I know it doesn't look much better, to be honest. That being said, everything in this equation is a constant, with the exception of this symbol, the lambda. Specifically, we have a dependence of 1 over lambda to the power of 4. What this means is that we have a really, really strong dependence on wavelength, lambda. This means that our longer wavelengths are going to result in a much, much, much smaller scattering cross-section than our shorter wavelengths. In other words, red light gets scattered much less than blue light. Now, when I talk about a cross-section, if you think of it like a hole, if you're trying to throw something into a hole, it's much easier to throw something into a large hole than it is to throw something into a small hole. And that is essentially what we're dealing with here. The red light scattering is like trying to throw the ball into the small hole. It's much harder to do because it's a smaller target. For the blue light, it's a much larger target just because of this wavelength dependence. What this means is that the red light, the light towards the red end of the electromagnetic spectrum, is going to have a much smaller scattering cross-section, making it much harder to scatter it, meaning it will not scatter anywhere near as much as blue light. So, now we know that blue light is scattered far more than red light, but that doesn't really answer our question of why is the sky blue and why do we get blue hour right before sunrise. For that, we need one more key concept: angles. Our planet exists in a three-dimensional space. Just because we can't see the sun doesn't mean that it isn't there. And when we can't see the sun, the light from the sun can still make its way through the atmosphere. So, when the sun is just below the horizon, its light is spilling up in a direction that, without the atmosphere, would just take it in a straight line past our line of sight and into space. However, we have an atmosphere. And what that means is that the sunlight gets scattered, and the blue light gets scattered more than the red, meaning that more of it is scattered towards the ground, towards our eyes. This means that just before the sun manages to peek its way above the horizon, that a load of this blue light gets scattered over the horizon towards our eyes, meaning we get this lovely blue hour that photographers love so much because it gives you some just really amazing photos. Similarly, when the sun is above the horizon, the light that would otherwise miss our eyes entirely by firing above over our heads into space gets scattered down by the atmosphere. And again, blue light gets scattered more, and this results in us seeing a blue sky, or at least a sky we perceive as being blue, because it's not scattering as much red light down towards us. But what about when the light is golden? We've talked a lot about blue light, and you think if blue light is scattered all the time, then we'd see that. But in the late afternoon, when the sun is low in the sky, we see this golden light, this much warmer tones. So what causes that? Well, it's also Rayleigh scattering. But the thing that you have to remember is that when the sun is really low in the sky, there is so much more atmosphere between your eyes and the sun. What this means is that most of the blue light, which is scattered more, has already been scattered down to be a blue sky for somebody else. What we're left with is these longer wavelengths, these reds and oranges and yellows that are much more difficult to scatter, and that's what reaches us as this lovely golden light that we love so much. So, that's why I had to get up so early to get these lovely blue hour photographs. It's why golden hour is so glorious right now. Thank you very much for watching. I hope you've learned something new. If you have, then please drop a like down below and pass this video on to a friend. If you're looking for something else to watch, then have a look at this video right here. It's an older video of mine where I explain how we know that there are lakes on Saturn's moon, Titan. In the meantime though, I am quite cold. I want a cup of tea, so I'm gonna go home. See ya.